Hello, I'm Ingrid Moerman from imec, where I am a member of the IDLab research group embedded in Ghent University. I am happy to explain you how the Horizon 2020 project ORCA solutions can help to speed up innovation for beyond 5G evolutions. In this video presentation, I will present some key solutions from the Horizon 2020 ORCA project. You can see here the main project facts and research partners that have contributed to the results. The key component in the ORCA project is software-defined radio, or in short, SDR. Innovation in 5G and also beyond 5G is driven by three core functionalities: softwarization, virtualization, and orchestration. Let us first have a look at softwarization. Softwarization is for sure a key driver for 5G. The development cycle of digital hardware is way more complex and time-consuming than doing all processing of radio and network functionality in software. Also, lifecycle management is far more easy for software than for hardware components. That's why the 5G architecture, at least for the infrastructure, promotes to shift the radio and network processes as much as possible to software that can run on commodity servers in the cloud. To this end, 5G has introduced the concept of functional split. Traditional wireless systems, as shown on the right, have the lower layer radio functionality integrated with RF front-end and antenna system, and only higher layer networking functions are centrally controlled. In the extreme softwarization case, shown at the left, the entire protocol stack is centrally controlled in the cloud, and the digital baseband signal is sent to a distributed unit called remote radiohead. Please note that digital baseband bitrate is typically 2 orders of magnitude higher than the actual user data rate carried by the baseband signal. This requires a very low latency, high bandwidth connection between the distributed unit and the central unit, and is implemented with radio over fiber technology. Radio over fiber comes with a high cost of deployment compared to the traditional, more embedded systems that can be interconnected by low-cost Ethernet or IP services. The 5G softwarized architectures allows more infrastructure sharing with more centralized control and is expected to lead to higher performance, but also to higher energy consumption compared to embedded solution. The much higher energy consumption is already a fact in 5G rollouts in China, raising high concerns about energy bills. In terms of performance, the centralized control by software processes in the cloud is great for non-real-time services and higher-level, more global decisions, important for mobility support and coverage. But for real-time services and low-latency connection, distributed decisions based on local information may be more appropriate, and for such real-time services, hardware acceleration closer to the antenna may still be a better option. Everyone claims 5G is great, but we also cannot ignore some observations. Softwarization is indeed great, but low latency will require less soft coding and more hard coding, meaning hardware acceleration, requiring a shift from CPU to GPU and FPGA, also requiring a shift of functionality closer to the antenna. This should not really be a problem, as embedded hardware is also reprogrammable, soft code as well as hard code, and hence softwarization still applies. Another observation is that research, innovation and experimentation in 5G has heavily focused on open infrastructure, but there is a lack of embedded open client devices that allow experimentation in dynamic scenarios with sufficient scale. End devices are very powerful nowadays and should also be involved in the design of end-to-end communication networks. A third observation is that smaller, local, and dynamic environments and niche markets may require more flexible and lower cost private deployments not operated by a public 5G operator. And finally, smaller players like SMEs are very important in Europe in terms of innovation and job creation, more important than large companies, and they should not be ignored. ORCA offers major, real-time and versatile software-defined radio platforms in advanced wireless test facilities. Let me further explain. If we look at this diagram, the horizontal axis shows performance, for example latency. The vertical axis shows the design cycle, which is inverse proportional to the degree of versatility and softwareization. Versatility means the combination of flexibility and reprogrammability. In the diagram we see that when going from CPU to ASIC implementation, performance increases, latency is reduced, but also versatility is reduced. Just as an example, latency requirement for LTE is 4 milliseconds, which allows a high degree of soft coding. On the other hand, Wi-Fi requires acknowledgement within 10 microseconds, which can only be achieved by FPGA or ASIC. 5G new radio is promising very low latencies and response times, which will limit the degree of soft coding. The goal of ORCA is to combine the best of both worlds by offering real-time software-defined radio, which combines high performance with high versatility. Let us zoom in on the lower layers of the wireless network stack, following the specifications of 3GPP. Traditionally, only the low-level 5 functionality is hardware-coded in FPGA on an SDR research platform, while most baseband processing and higher-layer functionality are implemented in software on a host PC. ORCA responds to the trend towards more real-time SDR implementation. This requires migrating more and more functionality to SDR platforms. As such, ORCA provides flexible methods to support future 5G beyond air interfaces and networking concepts, well before commercial platforms are available on the market. ORCA offers end-to-end networking experimentation with real-time SDR. Common SDR approaches are generally limited to 5 functionality and do not always allow real-time behavior. ORCA, however, offers full-stack end-to-end solution with prime focus on PHY and MAC, which is okay, as PHY and MAC are most challenging for achieving real-time behavior, while higher networking layers can be easily implemented in software. A typical SDR system has different types of architectural components where processing can take place. First, we have the antenna and RF front-end, which are analog components. Then we also have a number of digital components, FPGA, microcontroller, host PC, and cloud. We can further make a distinction between software and hardware programmable components. ORCA offers not only a full-stack data plane, but also the control plane that allows to interact with all processing components for configuration and monitoring. ORCA further supports both centralized and distributed control. Finally, ORCA has also solutions for live reprogramming, not only of the traditional soft code, but also FPGA hard code. Reprogramming over the air is also possible for end devices. The full ORCA architecture enables to control in real time multiple networked SDRs in multiple advanced experimental testbeds, allowing experimentation beyond single link in realistic scenarios. On top, we see an example of massive MIMO configuration, and one host PC controls many identical SDRs with local MAC support. Below is another example for millimeter wave SDR with phased array with centralized MAC support. Let me present you some more concrete examples of softwarization in ORCA. In ORCA, we have full-stack SDR platforms acting as Wi-Fi access point, IoT gateway or LTE base station that can communicate with commercial off-the-shelf nodes. This allows easy customization on top of well-proven wireless standards. Here is an example of customization. You can see in the table that the performance of our ORCA SDR solution is at least as good as commercial IoT devices. An IoT radio can be easily tuned by changing sampling rate and bandwidth, for example to increase reliability or to reduce latency, just like 5G new radio. ORCA offers the first free open source full stack Wi-Fi implementation on FPGA with Linux driver. Our implementation is fully compliant with standard Linux software for upper MAC and higher network functions. Real-time experimentation with SDR can be as easy as doing simulation. ORCA has developed an interface to connect NS3 simulator with LTE, Wi-Fi and 5G radio platforms. ORCA offers flexible, low-latency, embedded MAC-PHY architectures where PHY and low-level MAC can be reconfigured in hardware and high-level MAC can be reprogrammed in software. To increase throughput and spectrum efficiency, ORCA has developed in-band full duplex capabilities with both analog and digital self-interference cancellation. As a last example, ORCA offers a compact millimeter wave system operating in the 5G millimeter wave band of 26 GHz. The transceiver PHY is implemented on a USRP platform. The 2.4 GHz output of the USRP is upconverted with an oscillator and is connected to a multi-beam antenna array with a 16 by 16 Butler matrix. This brings us to the second key component for wireless innovation, virtualization. Network slicing is a way to provide isolated subnetworks, each optimized for specific types of traffic characteristics on top of a shared physical infrastructure. Virtualization is creating the illusion that each virtual network has its own isolated infrastructure. Network slicing facilitates network optimization for different use cases in different verticals. Network slicing can be achieved by software-defined networks following a centralized approach for controlling different network slices. ORCA extends the capabilities of SDN by bridging real-time SDR and SDN. It enables fine-grained control, monitoring and configuration at radio and network level to meet end-to-end application requirements. ORCA extends the network slicing concept to the radio level by mapping of radio resources to SDN flows. ORCA offers more fine-grained radio controlled compared to fully centralized SDN solutions. Again, we can illustrate with some more concrete examples. This example shows LTE infrastructure sharing. This allows multiple tenants to use the same eNodeB infrastructure. The solution has obtained a runner-up Best Paper Award at WinTech in 2017. In this example, we show how ORCA solves the IoT gateway bottleneck by virtualizing a transceiver on FPGA. Up to 8 fully independent, concurrent transceivers have been demonstrated, using the same footprint as a single transceiver, and with the additional advantage that all 8 transceivers are perfectly synchronized. A last example is many-to-many spectrum virtualization, allowing to maximally exploit available radio hardware and spectrum. In this example, 3 individual streams are shared on 2 radio front ends supporting different spectral bands. Multiple streams can concurrently share a single RF front end through partitioning of the spectrum, or one stream can be split into different non-contiguous bands by aggregation of RF front ends. This brings me to the last key component, orchestration. Softwarization and virtualization are enabling techniques for orchestration of radio and network resources in order to provide network services in an efficient, flexible, and scalable way. In 5G, network slicing is mainly led by NFV SDN communities promoting central coordination. However, efficient spectrum sharing and radio slicing requires fine-grained local control in the wireless domain, as has been successfully validated by Team Scatter, which consists of 2 ORCA partners in the DARPA Spectrum Collaboration Challenge. We believe that orchestration would benefit from domain-specific expertise, not only from the SDN and NFV community, but also from radio experts. That's why I would like to finish this presentation with the ORCA end-to-end vision. Different networks are built for different purposes, for example in terms of coverage, latency, and data rate. Different segments in a network can further consist of different media, for example optical, cable, wires. The main challenges are how to combine these segments into end-to-end slices and how to guarantee sufficient fine-grained resource control in the different segments. We further know that wired and wireless networks have a very different behavior. While wired networks are much more predictable and have a well-known capacity, wireless networks are unpredictable due to the inherent stochastic nature of the wireless medium, due to interference, due to mobility, etc. Wired and wireless networks can hence not use the same abstractions and models. The ORCA vision has been published as a white paper on the ORCA website. In the ORCA vision, we believe that each network segment should have their own orchestrator tailored to the segment's particularities. In this example, we have a wireless and a wired network orchestrator. The wireless orchestrator is in charge of instantiating radio access technologies by deploying the necessary radio functions. The wired network orchestrator is in charge of provisioning paths and deploying services in a wired network slice, building, for example, on SDN and NFV technologies, and more slices can be orchestrated. This is not sufficient. We also need hyperstrator functionality, which can be seen as the orchestrator of orchestrators. This could be a centralized entity, but more likely this will be a distributed functionality implemented as an intelligent distributed cooperation plane. The cooperation plane is responsible for interaction and negotiation with the segments, triggered by service requests from end-to-end applications. Service requests will be translated into segment-specific requirements based on information of available resources from potential segments. The most appropriate segments can be selected and composed for delivering the end-to-end service. Individual orchestrators can further follow their own processes and implementation for executing their own part of the end-to-end service and partitioning in slices. The ORCA end-to-end vision has several benefits. First of all, it is modular with specialized segment orchestrators designed by domain experts. It is robust and hence less vulnerable to single point of failures. Segments can be easily upgraded. It is extensible, allowing easy integration of orchestrators that manage new types of network segments. Very important, it is technology neutral, as it is not restricted to specific technologies, technology implementations, or specific spectral bands. It allows simplified standardization because the focus is on open, descriptive, and technology-agnostic interfaces rather than standardization implementation details within segments. Such an approach yields more freedom for solutions and implementations within segments and minimizes the risk of dependencies and lock-in. Which brings me to the end of this presentation. I hope I could convince you that SDR can boost innovation in infrastructure as well as in end devices. SDR enables rapid prototyping of full end-to-end solutions well before commercial equipment becomes available on the market. SDR is also accessible to the broader research community and SMEs. Please have a look at the ORCA website for the full offer.